We're in Rosen, Discrete Mathematics and its Applications, section 12.4 on circuit minimization or Boolean expression minimization. We will discuss Karnaugh maps in this sequence of videos. We will not discuss Quine-McCluskey. And circuit minimization can also be thought of as Boolean function or Boolean expression minimization because a circuit is just an expression of a Boolean function. For instance, if we have this Boolean function, which is the sum of two 3 literal minterms, is there a way that we could express this with a smaller or more efficient means? It turns out that there is, because we can factor out the x and the z from each of these, and that would be x times z um, times the sum y plus y bar, which equals 1. And so we can show that this equals x times z, minimizing it. That's a much easier expression to deal with than the other one. Simpler circuit as well. How about this one? We've got 4 minterms with 3 literals each, but note that we could factor x out across all of them, and the resulting product in the parentheses would always sum to 1, which you can verify on your own, so that this sum of products is actually just equal to x, which is a nice minimization of that much larger expression. And we did this because we could identify Boolean variables whose values didn't affect the outcome. Up here, y and y bar was in there, so the value of y didn't matter. Here we had every combination of x and y, of y and z, so that the values of y and z didn't matter, only the value of x mattered. And an efficient way for finding these variables whose value didn't affect the outcome and separating them from those that do are the use of these Karnaugh maps, or we'll call them K-maps for short. All right, well, what is a K-map? Well, K-map is actually similar to a Boolean table for a Boolean function, because it identifies where the function is equal to 1 or a 0, but they're specifically created for sum of products expansions so that we can minimize them. So more specifically, a K-map is a two-dimensional grid, and we represent 1 or 2 variables depending on the degree of the function in each dimension, horizontally and vertically. And we order them such that the complementation from row to row or column to column is only changed on one variable at a time, and I'll demonstrate this. Okay, so there's a cell for every possible value of the function. In a table, it would be one value per row. In this case, it's going to be one value per cell. It is possible to have a three-dimensional K-map, but we don't discuss them here. Okay, now each cell represents a value, 0 or 1, because these are Boolean functions, of the sum of products for the minterm represented at the intersection of the row and the column of that cell. So we'll be able to tell which combinations of literals and their complementations represent that value of 1 or 0. Now that we have this grid, we want to use power of 2 sized groupings of the ones. We're looking for the ones to identify ways that we can collapse the sum of products expansion into a minimized expression. All right, so the way we're going to do this is we're going to cover ones with largest possible groups, and it's okay if these groups overlap. But once we've covered all the ones, we can write down the minimized function. And then we're going to look at these groupings and figure out which variables don't change, just like on the previous one, the x didn't change in that 4 minterm sum of products. And then those variables that don't change will be the minimized expressions for that group. All right, let's do an example. The simplest examples will be the two variable K-maps. We've got three examples here, and first of all, let's identify the sum of products that we're going to be minimizing. Here's three sum of products and two variables that we'll be minimizing. We'll start with the leftmost one first. So I have my variables are x and y, and I let y be the horizontal dimension and x be the vertical dimension. And then I fill this out where the value is 1. So if x and y are 1, I get a 1 here. If x bar and y are 1, I get a 1. Sorry. If x and y are 1, I get a 1 here. And if x and bar and y are both 1, I get a 1 in the lower left. And that's all the ones that'll be in this table. And now I've got a grouping of 2 because 2 is a power of 2. And I group those together like this. And what doesn't change in that grouping? Well, x changes in its complementation, but y doesn't change in its complementation. And so the minimized function for a is just going to be a y. We could also do that with factoring. All right, so we've used a k-map to minimize that first Boolean expression. Let's look at the second one. So when x is 1 and y bar is 1, I get this one. And when x bar is 1 and y is 1, I get that as a 1. And it turns out that these groupings have to be contiguous and compact. And so the largest grouping I can cover these ones with are groups of size 1, that is 2 to the 0 power. And nothing changes in these, so x bar doesn't change and y bar doesn't change. Y doesn't change for this first one, and x doesn't change and y bar doesn't change for this second one in its complementation. So it turns out this function is already minimized. I can't simplify it any further. All right, this third one, I've got 3 min terms that I need to represent. When x and y bar are 1, I get a 1 here. When x bar and y are 1, I get a 1 here. And when x bar and y bar are 1, I get a 1 in the lower right. Well, now I can cover all of the ones with 2 groups of size 2. 1 here and 1 here. Now all of them are covered. Now I can write down the minimized functions. Well, in this vertical group, the thing that doesn't change complementation is y bar. In this horizontal group, the variable that doesn't change complementation is x bar. And so I can write down the minimized function as x bar plus y bar, which is a nice increase in efficiency compared to the 3 min-term sum. That is it for 2 variable k-maps.